So now we're in Unit 3, which is chapters 5 and 6 in the book, and this is going to be all about forces. And you do have some homework tonight. I want you to do through number 15, so you can hold off on 17, but they're actually mainly vector problems, so it should sort of be old stuff. Anyway, so far we've studied kinematics, how objects move. We can figure out the distance something travels, or its displacement, its time, its final velocity, initial velocity. But why are they moving at all? Now we're going to study dynamics and the forces behind motion, which sort of laid out to us by Sir Isaac Newton in 1687 with his 3 laws of motion, which I know you've learned before, but we'll go back through them. First few definitions, which I guess you've already got written down for you. A force is a push or a pull. And of course, a force is related to an acceleration, which we know through Newton's second law. But a force is a vector. So pay attention. Don't try to go through problems too quickly where it says, Emily pulls 5 newtons north and Erica pulls 5 newtons east on a book. What's the net force? What's the total force? You can't just say 5 plus 5 is 10. Okay, if you've got directions like that, you've got to deal with your components, and you do a little trig there. So just be a little careful on that. But you got your books handy, hopefully. A few checkpoints that we'll go through. This is in chapter 5. Did I not put a page number? Apparently not. Nope. Well, let's see if we can figure it out. All right, checkpoint number 1. In the figure below, 2 perpendicular forces, F1 and F2, are combined in 6 different ways. Which ways may be used to correctly determine the net force between them? So just your basic vector knowledge, vectors are added head to tail. Even if we don't necessarily draw them like that, can you visualize which ones would be added up head to tail to equal that resultant or net force? Correct. C, D, and E. All of those, if you add them head to tail, would give you that final resultant. Any questions on those? You had one of those in your last test, on your last test. Okay, we understand adding head to tail. So forces are vectors. Add them head to tail just like we did any of the vectors in the last unit. The SI unit for force is a Newton, after Isaac Newton. What does a Newton actually break down to? Well, since the second law is mass times acceleration, F equals ma, you're going to take your SI mass unit, kilograms, and your SI acceleration unit of meters per second squared. So it's the amount of force to accelerate a 1 kilogram object. Remember, in that 1 kilogram is about 2.2 pounds, to 1 meter, or at a rate of 1 meter per second squared. So if something was still, the force I need to accelerate it to 1 meter per second after a second. So it's not too much. Net force, the sum of all forces acting on an object. Just sort of went over that. All right, equilibrium. And I guess I'll fill it in since you have it. Equilibrium, it's got a bunch of meanings in science, but it sort of means what? Equal, the same, balanced. So it's a state in which your net force is 0. Doesn't mean there aren't any forces, they just all balance out. Now, in equilibrium, objects can move, and that's something that gets mistaken a lot. Just because something's in equilibrium doesn't mean it's still. It could. Like right now, I am not moving, but there are forces acting on me. Can you name the forces acting on me? Gravity. The force of gravity, which would be my... Starts with a W. The force of gravity on an object is called that object's weight. Okay, so my weight's pulling me down. What's pushing me back up? The ground. The floor itself, Because if the floor wasn't here, well, then I would be falling. But the normal force from the floor, so I'm in equilibrium. So I am still, that's fine. But other examples, maybe somebody in an elevator. Now, not the beginning and the end of the elevator, but in the middle, moving along at a set, steady pace. Well, there's still the weight of that elevator down. There's a tension force pulling that elevator up. And if they are balanced, well then the object is simply not accelerating. So if there is a net force, the objects will accelerate. If there isn't a net force, there's no acceleration. But something could still move, just not accelerating. All right, our 9th grade pictures. You have the answers, don't you?
Yep.
What's the net force on the first one?
0.
Nothing. How about over here?
2 to the right.
Very good. Specifically 2 to the right. Here?
1 up.
1 up. Here?
0.
0. So which will have the greatest acceleration?
2 to the right.
Yeah, this is your biggest force, 2 newtons to the right. Whoa. Which ones won't accelerate? Yeah, these two. Could still be moving, but they're not accelerating. All right, 87. I'm actually going to 3, and then we'll go back to 2. But skip over to 87 just for a second. Sort of the same thing. It says the figure shows overhead views of 4 situations in which 2 forces accelerate the same block across a frictionless floor. And just for the most part, Chapter 5 is going to be frictionless. And then Chapter 6 will add in friction. Rank the situations according to the magnitudes of the net force and the acceleration greatest first. So, Zach, looking at all of those boxes, and they're all 2 forces of 3 and 5. But which one's going to be the greatest net force?
Greatest net force?
Yep. Yeah, number 1. That's going to give you a net force of 8. So there's no other way we could get a bigger force than 8 with forces of 3 and 5. What would be after that, Zach?
The greatest acceleration.
Yeah, well, no, the next greatest force. So 1's definitely the greatest force. What's?
4. 3. The next greatest force?
Yeah, is it 4 or 3?
3. 4? I don't know.
It is 4. Yeah, because the 3 is like sort of going in the same direction of the 5. There is an x component there. And if you just try to imagine adding those arrows head to tail, your hypotenuse is going to be bigger for 4 than it is for 3. If you can kind of visualize that. All right, and then obviously 2 would be the worst because they're opposing each other. So the accelerations, of course, all match. 1, then 4, then 3, then 2. I'll just draw that one. Maybe. Maybe. So we had 3 and 4. And this one was just kind of like that. So if you're adding them head to tail, can you see? This one had to be bigger. All right, moving right along. Newton's laws. Remember the titles of them? Oh, of course you do. All right. So we've got the law of inertia, F equals ma, and action-reaction as our most basic little titles there. Going to go through each of them. The law of inertia, well, first of all, our definition of inertia. Resistance to change in motion. Whether that be motion that is still or motion that is moving, how difficult is it to change what that object is doing? If it's an airplane that's still and I want to get it moving, Well, it's going to be difficult because it has a lot of mass, it has a lot of inertia. Or if that airplane was moving at 200 miles an hour, getting it to change from that velocity as well would be difficult because it had a lot of mass. A mouse, on the other hand, much less inertia. Sorry. So if you have no net external force, we were just talking about this, it is going to be moving at a constant velocity, which could be still, but it's not accelerating if there's no net force. All right, back to the book, 85. Checkpoint number 2. Back to our forces of 3 and 5. Daniel, this one's for you. All right, so the figure shows 2 horizontal forces moving a block along a frictionless floor. Assume that a third force, F3, also acts on the block, but it's not drawn. What are the magnitude and direction of F3 when the block is stationary? So what third force could you add to make that situation still?
2 to the left.
Exactly, 2 to the left. What if I wanted to move it to the left with a constant speed? What third force could I add? Okay, now almost a trick question, because you have to realize there would have to be some net force to get it going. So, but let's say it just is moving now, for whatever reason, at 5 meters per second to the left. To make sure it stays moving at 5 meters per second to the left, what third force is necessary? The same answer, exactly. They would still have to be balanced either way. I do understand, though, there obviously has to be some net force to get it moving, to accelerate it in the first place. But to keep it moving at a constant velocity would still be the 2, because that would balance our system. That would put it in equilibrium. And constant speed, constant velocity is kind of a key word you're going to want to look out for in your problems. So if it ever says something's moving at a constant speed or constant velocity, you know all the forces are balanced. All right, law of inertia only holds true for inertial reference frames, which we will only be dealing with anyway. And we've sort of talked about this already. 2 observers might view the motion of an object differently, like somebody in the elevator or like the guy filming the cheetah on the truck. But they should still have the same conclusion as to the net external forces, which makes sense from last unit when we said they should still have the same conclusion about the net acceleration. You know, I might see the cheetah as changing speeds between 0 and 60. Somebody else might see the cheetah as changing speeds between 10 and 70, but it's still going to be the same change, the same acceleration, even though we observe different speeds. So I'm on the ground, I see a tree at rest. You are in a car moving at constant velocity and see the tree as moving at 50 miles per hour, although of course we know we're the ones moving relative to the ground. We should still both conclude that there are no net external forces acting on the tree, because constant velocity and rest will both be clues that there's no net force. Okay, so that was law 1. Law 2. Law 2 is essentially our formula. F equals ma. And the direction of the force should match the direction of the acceleration. They're vectors. Make sure, though, if there's 17 different forces acting on your object, that to use this formula you found the net. You've done the vector sum of all of them, gotten that resultant, and you're just using the net force. You don't just get to pick your favorite force to plug in here. It's got to be the total, the net. So the net force on an object is proportional to its mass times acceleration. And if we need to, we can break that down into components. All right, and our third law, last law, action-reaction. If 2 objects interact, the force exerted by object A on object B is equal and opposite. Equal in magnitude and opposite in direction. to the force exerted by object B on object A. So that means right now, you guys told me there were two forces acting on me, my weight and the floor. Well, why do I have weight at all? Because there's gravity from what? The earth. Okay, the earth is pulling me towards it. What is equal and opposite to that? Just keep the two objects, me and earth. I'm pulling on the earth. Not noticeably so, but if the earth is pulling on me, I am also pulling on the earth. If I jump up, the earth pushes me up, I push the earth down. Not noticeably so. And then we pull each other back together and we land back where we were from the get-go. Yeah?
What was the whole scenario like if everybody in Japan, or not Japan?
If everybody gathered on one side of the earth and we all jumped,
Yeah.
what would happen? Well, everybody would jump up a little bit and the earth would move the opposite way a little bit. Then, since we both have mass, we both have gravity, and we're both pulling on each other, so we would pull right back together to where we were. I don't think, we could look it up, I do not think that would be enough force to like knock Earth out of its orbit or anything like that. But
Why doesn't the gravity of the sun affect our weight?
it does.
It does?
I mean, yeah, technically everything affects our weight. I mean, I'm being pulled down to the Earth right now, but I'm also being pulled up towards that ceiling since it has mass. I'm also basically being ripped in all directions because that wall's pulling on me, that wall's pulling on me. But compared to the entire mass of the Earth underneath me, that's all pretty much negligible. All right. So when we do talk about action-reaction like that, you do need to think of the two force pairs, the two objects we're even talking about. You know, a hammer hits a nail, okay, well, a nail provides a force back on the hammer. Vice versa, like a book in the earth or me in the earth. The earth is pulling on me, I'm pulling on the earth. Don't throw in an extra object. Don't say the opposite force is the table pushing back. No. The opposite force isn't the floor pushing back. That is another force, but it's not the pair we're looking for. All right, types of forces. A force can be, you know, any push or pull, and you can label it accordingly. Anything that sort of makes sense, like, you know, you could just call it FP for F pull. But there are some common ones we sort of label with these variables. Weight, of course, is W. In fact, for tonight's homework, I do want you to, oh, never mind, it's on the next page anyway. I wanted you to write down the weight equation, but it's right there. All right, so we have weight, normal force, friction, tension, and then any other force we want to label appropriately is fine. But weight is usually labeled with a capital W, which will be slightly confusing later when we study work, but we'll know the difference. The formula for weight, it is just a spin-off of Newton's second law. A force equals a mass times an acceleration. Well, if I specifically pick the acceleration of gravity, that's an object's weight. So it's gravitational force. And it is a natural force of attraction between any two bodies. And we'll have a whole other chapter towards the end of the year talking about universal gravitation. But for now, we're just going to pick our weight on Earth. We'll use the gravity here on Earth. If we use the moon, we'd have to pick a different. We mentioned this before too. Make sure you know that, well, if weight is based on gravity and you go somewhere where gravity is different, like the moon, is your weight the same or different? Different. Is your mass the same or different on the moon? It's the same. You know, that's sort of the number of atoms and molecules that make you up. If you go to the moon, presumably you are still made of the same atoms and molecules. So you would have the same mass but different weight. And hopefully you'd be safe on the moon. All right, dealing with weight on an incline. we will need to do this in some of our problems. Come on. Yeah. We'll get into some drawings, maybe at the end of today or next time. Free body diagram is going to be a big part of dealing with forces, making sure we draw a good diagram for what's going on to indicate all the forces acting on something. But if we have this box on an incline, on some ramp, which way does weight pull it? Straight down. Weight always pulls something straight down. That's not my best straight down, but I'm going to do better. Now, that might not be a convenient vector to work with if we're dealing with the rest of the motion of the box, which is probably parallel. The box is going to be going this way. So this vector is clearly not in the same line as this vector. But what we can do when we deal with weight on an incline is we draw the components of it. So this is just the weight straight down, which you can get by doing mass times gravity. Pen, come on. But we can draw these components. Do you know these are the symbols of? You know this one. Okay, parallel, perpendicular. So once you draw your weight, and I always draw it this way. Again, it doesn't matter which one you draw first, but I always like to draw the perpendicular one first. And when I say perpendicular, perpendicular to what? Perpendicular to the incline itself.
So if you were to make a vector, would you just connect it to the very top of the incline?
I'm trying to make a vector diagram out of weight. So where weight actually is the resultant. So I've got my perpendicular component, and here is my parallel. Again, parallel to what? Parallel to this, to the incline. Because remember, a vector can be the sum of any other vectors you want it to be the sum of. Obviously, pick vectors that are helpful to you. The reason why this is helpful is, well, if the motion is parallel to the incline, well, then I want to deal with forces that are parallel to the incline. So I would want to deal with weight parallel. And just like when we did projectile motion, once you find these components, you are done with the weight. Do not throw that number back into your problem. You're going to deal with weight parallel or maybe weight perpendicular if you need to. But probably this will be the useful information if you're dealing with motion this way. Although we almost inevitably need to find weight perpendicular anyway. Remember that the parallel is parallel to the incline here, the diagonal part, not this part, because that would not give you a right angle. Okay, so that's weight, normal force. So we use capital N. It's really just the force from a surface. There's a force from this floor pushing back on me. That's why I'm not falling through it. It's not pushing me sideways. It's just pushing me straight up. It is always perpendicular to the surface itself. So if you have an incline again, the pen just does not always like me. You have an incline, the normal force, don't make it straight up. Make it perpendicular to that incline. I like to go with capital N. So for flat surfaces, assuming there wasn't an additional like upwards or downwards force, like just a book sitting on a table, me standing on the ground, my weight down would equal the normal force up. And when we're talking about force, we're just talking about the forces acting on one object at a time. Yes, I am pushing on the floor, but for the most part, that's usually like irrelevant. I just care about what's going on with that object. I know there is the equal and opposite forces. I'm pushing on the floor is pushing on me. But if I'm just talking about this box, or I'm just talking about me, I only care about the forces acting on me. All right, 89. Whatever 89 is. 4 first. And this one's going to Emily. All right, in figure 5.8, which is where? Oh, just the box sitting on the table. Is the magnitude of the normal force N greater than, less than, or equal to the weight magnitude if the body and table are in an elevator that's moving upward at a constant speed? So, draw it. Here's our elevator. Here's our table. Here's our box. So there's a lot of forces going on. There's some cable, there's a tension in this cable pulling the elevator up. But I don't care about all that. I just care about this box. What forces are acting on this box? Normal force and weight. And if they tell you that it's moving at a constant velocity, what must be true about the normal force and the weight? They must be equal. Perfect. Now, what if it is moving upward at an increasing speed? The normal force would be bigger. It would have to be bigger because you're increasing upward. If you're accelerating upward, you must have a net force upward. Which is neat if you ever just happen to have a bathroom scale in an elevator. When you sort of accelerate upward, the weight, you're almost reading the normal force, but the weight will read bigger when you're accelerating upwards. A few more forces. Friction. You know what friction is. Friction is the force that opposes motion between two surfaces. It is always opposite the direction of the motion. Friction can act, though, when something's not moving. But you have to ask yourself the question, would that thing be moving if friction wasn't there? If the answer is yes, then friction must be present. A good case would be an incline problem. Okay, flat desk, I can lift the desk up a little bit. I've got a decent incline. Shouldn't that book be moving? Why isn't it? Friction, okay. So friction can apply in cases where objects are still, but you have to ask yourself that question. Would it be moving if friction wasn't there? If the answer is yes, then friction's there. All right, tension is just sort of how we label any force from a rope or a string or like an elevator cable. All right, and I guess we're back to 89. Shouldn't have shut it. All right, Thomas. A body is suspended by a rope in figure 510C. Okay, so this is a pulley situation. It has a weight of 75 newtons. Is T equal to, greater than, or less than 75 newtons when the body is moving upward at a constant speed? Equal. Because there's only two forces, tension up, weight down. Constant speed means it's got to be equal. How about B? It's moving at an increasing speed upwards. Yeah, the tension's got to be the bigger force there. And decreasing speed? Yeah, less than. Okay. We'll do a few labs, actually, with the setup kind of looking like this. And we'll do a pulley lab, another pulley lab. But some hints when you're dealing with tension. If you have all these objects tied together like so, and from the looks of it, which way is the system going to move? Yeah, we've got more mass over here, so it looks like it's all going to move to the left. What would be the same about all of these objects? if they're all tied together. And forces and masses aren't the answer. Very good. That's all written down? Well, come on. Good job, Connor. All right, they all have the same acceleration. They have to, otherwise they'd rip apart. But assuming they're not ripping apart, the way that you would tie all of these different scenarios together, each object together, is through its acceleration. So when we're studying forces, we usually just study one object at a time. And if we do need to relate them, in this case it would be through their accelerations. They would have all the same A. And pulleys, are Atwood's machine. They're also called Atwood's machine. A pulley is simply used to redirect the motion of an object. Of course, we study mechanical advantage in 9th grade, but we'll deal with just very simple pulleys here. Okay, and we'll finish up with free body diagrams next class.